This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Ministry of Aeronautical Engineering, Hyderabad. Today we are discussing shear force and bend moment diagrams for the simple supported beam subjected to point loads in mechanics of solids. Types of beams. The beams are classified as cantilever beam, simple supported beam, overhanging beam, rigidly fixed or built-in beam, and continuous beam. First one is a cantilever beam. A cantilever beam is the beam which is fixed at one end and a free hand other end as shown in the figure. The distance between the fixed end and the free end is the length of the beam. Simple supported beam. A beam which is freely supported at both the ends is called simple supported beam. The supports, it may be knife edged or the roller supports. The moments at the supports are treated as zero because it is freely supported. The distance between the supports is treated as the length of the beam. The overhanging beam, a beam freely supported at any 2 points of its length and having one or both the ends projected behind the supports is called overhanging beam. The beam which is shown in figure, here it is the A and B is treated as the supports. The beam is here projected on both the ends, but in figure number B, it is projected at one end. That means it may be projected at both the ends or one end of the support. The fixed beams, a beam which is having both its ends fixed or built-in walls as shown in figure is called fixed beam. A fixed beam is also known as built-in or encasted beam. Continuous beam, a beam which is provided more than two supports along its length as shown in figure is called a continuous beam. Cantilever, simple supported beam, the beam in which one end is fixed and other end is supported by using knife edge or roller as shown in figure is known as cantilever simple supported beam. These beams are always subject to the loads. These are called vertical loads. Sometimes the reactions offered by the supports are also treated as the loads. These loads are classified as the point load or concentrated load, uniformly distributed load, uniformly varying load. Sometimes the beam also subjected to the combination of point load, uniformly distributed load, or point load, uniformly varying load, or it may be the combination of uniformly distributed load and uniformly varying load. Now we are taking simple supported beam with a point load at its midpoint. Consider simple supported beam A and B of span length L carrying point load W at its midpoint C as shown in figure. Here this is representing the cantilever beam. It is represented its ends A and B of length L. It carries a point load that is W at its center C as shown in figure. Now in the previous discussions, the reactions offered by the supports are also treated as the loads which are acting on the beam. And so while drawing the shear force as well as the bend moment diagrams, we have to determine the magnitude of the reaction force at A and B now. Since the beam is under equilibrium by the action of the reactions at A and B as well as the W at its center. When it is in equilibrium means the sum of the forces which are acting along the x direction should be equal to 0, and the sum of the forces acting along the vertical direction also 0. And third condition is the moments created by these forces at any point should be equal to 0. So according to these conditions now, since there is no horizontal forces acting on it now, hence it is limited to only two equations. The sum of the vertical forces should be equal to 0, and second one is the moments created by these forces at any point should be equal to 0 now. So for this figure now, figure number 1, the sum of the vertical forces is equal to here now. The reactions at A is equal to assume RA, the reaction at B is equal to RB. These are acting upward directions and W is acting downward directions. Hence RA plus RB, it should be equal to W required now. Okay, it is equation number 1. The second one is the moment created by the forces at any point should be equal to 0. That is, I am taking the moments at A, some of the moments. Here RB is, tends to rotate the body in anti-clockwise directions. It is equal to assume positive RB into L, and the point load tends to rotate the body in clockwise directions. Assume negative W into L by 2, it should be equal to 0 now. From these relations now, RB is equal to, we can take it as W by 2 now. Similarly, RA is also equal to, because RA plus RB is equal to W, hence RA is also equal to W by 2 now. So we got the reactions at RA and RB, which is equal to W by 2. R is also equal to 0.5 W as shown in figure now. Now we have to draw the shear force diagram. So here the shear forces, with respect to the left hand side of the beam, that is A, the forces which are acting upward directions are treated as negative forces, and downward forces are treated as positive forces. Or in other words, we have taken one statement earlier now. The effect of the force, if it is tends to slide the left hand side of the portion of the beam upward directions, then that force is treated as a positive force. Here the W is it is there now. Because of this effect, the lower side, that is the right hand side of the beam, is moving downward directions, and upper side is left hand side portions, hence W is treated as positive now. That is pointed. In the same way, the RB, it always tends to move the right hand side of the portion of the body upward directions, left hand is downwards, hence it is treated as negative now. That means here, according to the sign conventions, the forces which are acting upward directions are treated as negative, and downward forces are negative positive with respect to the left hand side of the beam, that is the A point. Hence, here RB is equal to, we can take it as minus W2. At C, it is nothing but plus W. And A to A is equal to, again, we can take it as plus W by 2 now. Now, from these relations, we got the shear forces. Here now, the shear force at distance of A, that is Fx is equal to, that is RA is equal to 0.5 W. The shear force between C and A, that is C and A, here at B is equal to minus of W2, Since there is no shear force acting between B and C, it remains constant. But at C, suddenly the W force is acting positive. But L is minus W by 2 plus W by 2. The resultant is W by 2. It moves upward direction. So, or in other words, at C is equal to minus W plus W by 2. As I'm moving from C to A position now, there is no forces are acting on it. Hence, the shear force is a constant up to A position, so as shown in figure now. So, here now, from this relations we got RA is equal to RB is equal to minus of W by 2. RC is equal to here now minus W by 2 plus W is equal to positive to there, and at A again W by 2. So, for drawing shear force diagram, first of all draw the lines, vertical lines passing through the point B as well as the C and A to represent the various section of the beam at which the forces are acting. So, the reference lines we are taking, this is known as here the axis of the beam there. At B, minus W by 2 force is acting in downward directions, hence it is treated as negative. It can be represented, the force can be represented both in magnitude and directions, but vertically downward the direction is there. The magnitude can be represented by using some suitable scale now. So, draw the vertical upward directions. Up to C, there is no between B and C, there is no forces acting now. And so, draw the horizontal lines up to C position now. At C, again, downward force of W that is acting now. That is the resultant force is equal to, now becomes at RC is equal to how much it is? Minus W by 2 plus W. It is equal to W by 2 now. And so, draw vertical lines upward direction to represent the resultant unbalanced force, which is equal to W by 2. Now, from C to BA, there are no forces acting, and so draw the horizontal lines to meet the vertical line passing through point A now. So, this diagram is known as shear force diagram for the cantilever beam. When it is subjected to a point load, it is a center now. The bending moment diagrams. The name of the beam is here now, simple supported beam. That is freely suspended at its supporting points, that is A and B now. That means there is no movements at these points now. Hence, the bending moment at A equal to 0. Similarly, the bending moment at B is also equal to 0. It is applicable for the cantilever beam when it is subjected to point loads or uniformly distributed load or uniformly varying load or the combination of any forces. This equation is the applicable. That is the MA is equal to the moment, bending moment at A is equal to 0. B is also equal to 0 now. Now we require bending moment at a point of C now. Here now at C. So, in order to derive the equations, generally we are considering a section at a distance of x. At x, the bending moment is created here is equal to force into distance RA into x. Here we have taken RA into x. RA is equal to W by 2 into x is shown in figure. But it tends to bend the beam in the form of concavity at the top. It is also called sagging effect. It is treated as positive now. When x is equal to the means 0, the means x is equal to 0 means that MA is also here, it is equal to 0 now. When x is equal to L by 2 now, that means it is treated as center of the beam. So, MC is equal to W by 2 into L by 2. It is equal to WL by 4 now. The bending moment varies from A to C now. From this point A to C, it only depends upon the distance moved from A to C position now. Hence, it follows a inclined straight line law now. That means at C we got bending moment is equal to WL by 4. Draw the vertical line WL by 4. At A is equal to 0. Hence, draw the lines in these directions. Similarly, the bending moment at any section between C and M at a distance of x is equal to, that is, if I take at a distance of x from A, it is equal to RAX. If I take the points at this somewhere at this position now, assume which is at a distance of x, it is equal to RAX, RA into x, but it now tends to deflect the beam in the form of concavity, and it is treated as positive. But here the point load is always there now. It tends to rotate the body in the form of convexity at the top, that is treated as negative, hence which is equal to minus half W into this distance is equal to x minus L by 2 now. So when x is equal to L by 2 now, that means nothing but treated as midpoint, we got already W by 4. But when x is equal to L, again it is equal to becoming 0 now. Or in other words, at the free ends at A and B, the bending moment is 0, and it is having maximum values of W into L by 4 at its midpoint. And from A to C, that midpoint is following the straight line law. Similarly, from B to C is also following the straight line law. And so for drawing bending moment diagram now, draw the vertical lines as usual, like shear force diagram. Put the moment at A is equal to 0, the bending moment at B is equal to 0, the bending moment at C is equal to W into L by 4. So represent these values according to the suitable scale, join A and C as well as the C and B as shown in figure now. Okay, this is the way of drawing shear force as well as the bending moment diagram for the cantilever beam when it is subjected to a point load at its center. When several forces are acting on it now, here the 2 points we are considering now, and this problems give the bending moment as well as the shear force diagram when the beam is subjected to 2 point loads on the beam. Here consider a simple supported beam AB, a span 2.5 meters, is carrying 2 point loads as shown in figure. Draw the shear force and bending moment diagrams for the beam. Here the given problem is the length of the span is equal to, that is the length of the beam is equal to, is given 2.5 meters. The point load at C is equal to 2 kilonewtons, which is at a distance of 1 meter from the end A, and W2, that is 4 kilonewtons at D, again is at a distance of 1 meter from the B end as shown in figure. Now, the first step to determine shear force as well as the bending moment diagram for drawing, the reactions at A and B require now. So, the procedure for determination of RA and RB, that is reactions at A and B, by assuming that it is under equilibrium now, under the action of RA and RB, the reactions as well as the loads 2 kilonewtons as well as the 4 kilonewtons. Since there is no horizontal forces acting on it, hence 2 equations are applicable. One is the sum of the vertical forces which are acting on the beam should be equal to 0. And second equation is the moment created by these forces at any point on the beam should be equal to 0 now. Based on the 2 equations now, assumptions, first assumption is the sum of the vertical forces acting on the beam should be equal to 0. Here RA and RB, they are acting upward directions. It should be equal to the sum of the downward forces, that is 2 2 plus 4, it is equal to 6 now. Okay, it is the equation number 1 now. So here, this is the equation number 1. The second one is the moments created by the forces at any point. Here I am taking the moments at a point now, which is represented as a sigma MA. It is equal to RB into, that is I am taking when this point. This RB is there now. It tends to rotate the body in anti-clockwise directions. Okay, some textbooks they given the anti-clockwise direction is a positive, clockwise direction negative, and so on. Now, this according to the book what I am following now. Here they have mentioned clearly the moments which are acting in anti-clockwise direction are positive and anti-clockwise direction negative are taken. According to this one, RB is nothing but the reactions tends to rotate the body in anti-clockwise direction positive. RB into the distance between the reference point to point of application is equal to 2.5. RB into 2.5 minus the 4 kilonewtons acting clockwise directions negative. Hence, here 4 into the distance between D and A is equal to 1.5. Here now it is there. And one more is here it is a negative. And 2 kilonewton is there now. Again it tends to rotate the body in clockwise directions. Again negative 2 into 1 now. Okay, from this relation we got RB into 2.5 is equal to 2 into 1 into plus 4 into 1.5. This value is equal to 8. RB is equal to 8 by 2.5, which is equal to 3.2 kilonewtons. Similarly, RE is equal to 2.8. Now draw the shear force and the bending moment diagrams. Okay, the procedure is just after drawing the beam according to the some suitable scale, draw the and represent all the forces which are acting on it. Now draw the vertical lines in downward direction. So for drawing shear force as well as the bending moment diagram. Now draw the suitable distance horizontal lines to represent the base or the length of the beam here and represent the points A, B, D and C as shown in figure. The bending moment, that shear force at B is equal to, already we determined its values is equal to RB is equal to 3.2. So select 3.2 kilonewtons to represent on a drawing a suitable scale. Here I am taking 1 kilonewton is equal to 10 mm. That means 3.2 is equal to 32 mm. So I am taking 32 mm in downward directions like this. Since there is no forces acting between B and D now, hence it is treated as a again at 4 kilonewtons it is there now. That is acting downward direction positive force. The upward forces are treated as negative already told now. So the resultant is equal to minus 3.2 plus 4. It is equal to 0.8. Hence draw the 0.8 upward direction. So that is the according to scale should be 8 mm. Since there is no forces acting between C and D now, hence draw the horizontal lines. Again at C now 2 kilonewton force is acting, which is a positive. The resultant now becomes 0.8 plus 2, 2.8 upward directions. Since there is no force acting, you have to draw the horizontal lines like this to meet the vertical lines at a point A now. This diagram is known as the shear force diagram. The bending moment diagrams. The bending moment at the free ends, that is at A and B, always equal to 0. That is MA is also equal to 0. Again, MB is also equal to 0 now. The bending moment at C is equal to, we can take the moments created by the forces at any toward the left side or right side now. So when I am considering point C now, I am considering the points, that is moments created by the A point, to avoid so many unnecessary calculations. So the bending moment at C is equal to, I can take it as 2 2.8 into just 1 meter. It is equal to moment at a point C now. It is a positive now because it tends to rotate the body in anti-clockwise directions, or it will deflect the beam in the form of concavity at the top now. It is equal to 2.8 kilonewton meter now. Similarly, the bending moment at D is equal to, when I am taking D point, I am taking the effect of the force at B now, that is equal to taking, which is also equal to 3.2 into the force into again 1, it is equal to 3.2. Since it is again, it is there now, the effect of this force is to deflect the beam in the form of U shape now, concave at the top, or it is also called sagging effect, hence it is treated as positive, hence it is equal to, I am taking 3 kilonewton meter now. The summary is the moment at A is equal to 0, at B is also equal to 0, at C is equal to positive 2.8 kilonewtons, and at D, that is 3.2 kilonewton meter. Okay, the conclusion is that the bending moment is always positive for the simple supported beam now. But the shear forces toward the right side, it is a negative, and toward the left side is the positive. Now, in order to draw the shear force bending moment diagrams, after completion of shear force diagram, extend this vertical lines still further now. Here now, at a suitable distance, draw one horizontal lines to represent the length of the beam. Here now, at A, the bending moment is equal to 0. At B, the bending moment is equal to 0. At C, it is equal to 3.2. Since the bending moment, because of the point load, it always varies with the distance only. Hence, you have to join these 2 points by straight lines now. Similarly, at C, it is there now. The bending moment at C is equal to 2.8. And so from A to, again we got 2.8. Afterwards, join the remaining points just by using the straight lines. This diagram is known as shear bending moment diagram for the cantilever beam when it is subjected to 2 points loads as shown in figure. A simple supported beam of length to 6 meters carries two loads 3 kilonewtons and 6 kilonewtons at a distance of 2 meters and 4 meters from the left end. Draw the shear force and bending moment diagrams of the beam. The given net in the problem is the length of the span is equal to 6 meters. The point load at C is equal to 3 kilonewtons. The point load at D equal to here 6 kilonewtons. The supports are acting at A and B now. So it can be treated as a RB as well as the RA now. Okay, first step in the problem is for drawing shear force and bending moment diagrams. Determine the reactions at A and B now. Since the beam is in equilibrium now, that is sum of the forces acting in vertical direction should be equal to 0, or in other words, the sum of the vertical force should be equal to the sum of the vertical force acting upward direction should be equal to the sum of the forces acting downward directions. Hence, RA plus RB both are acting upward directions. It should be equal to 3 plus 6, which is also equal to 9 kilonewtons now. And one more equation is the moments created by these forces at any point should be equal to 0. Generally, preferable is always the left hand point now. The moments created by the forces RB 6 kilonewtons and 3 kilonewtons at C, it should be equal to 0 at a point A now. So MA is equal to, we are taking now the moments which are tends to rotate the beam in anti-clockwise direction are treated as positive and clockwise direction are treated as a negative now. So here now the moments at A is equal to MA equal to RB into the length of the beam is equal to the distance between A, B is equal to 6 meters now. RB into 6. It is a positive because it tends to rotate the body in anti-clockwise directions. Similarly, 6 kilonewton is there now. With respect to it tends to rotate in clockwise direction, hence it is a negative. That is 6 into 4 negative minus 3 into 2 negative. But the sum should be equal to 0 now. So from this relationship we got to RB is equal to RB into 6 is equal to 30 or RB is equal to 30 by 6 which is equal to 5 kilonewtons. But RA plus RB is equal to 9 now. Hence RA is equal to 9 minus 5 which is equal to 4 kilonewtons now. So after determine the forces at A, B, C and D now, draw the shear force diagram. So in order to draw the shear force diagram, first draw the beam as per the suitable scale now. Draw the vertical lines, downward directions from the various points where the forces are acting now. At suitable distance, draw horizontal line to represent the length of the beam. Now with respect to the point A now, according to sign convention now, the forces which are acting upward direction are treated as negative and downward forces positive now. So this is the sign convention for the shear force. So at B, the upward force is there now, which is equal to 5 kilonewtons now. So from B, draw vertical lines that 5 kilonewtons downward directions by using some suitable scale. Here I am taking 5 kilonewtons nothing but equal to here 50 mm. 1 kilonewton is equal to 1 centimeters now. So 5 centimeter downward directions. After that, from B to D there is no forces acting. Hence draw the horizontal lines up to D position now. But at D suddenly 6 kilonewton force is acting. Again downward direction, that's a positive. Here 5 is a negative, 6 is a positive. The remaining resultant force is equal to 1 kilonewtons. That is 1 centimeter up. So draw the up to 1 centimeters upward directions. There is no forces acting between B, C and D. So again horizontal directions. At D again 3 kilonewtons acting downward directions. Again it is a positive. So you have to take 30 mm upward directions. And there is no forces acting between C and A. And so draw the horizontal lines up to this position now. This diagram is known as a shear force diagram. Generally, it is actually at an angle just inside the diagram for the representations. Bending moment diagrams. The bending moment diagram is shown in figure here now. 14.C we are taking now, and the values are determined as given below now. So the shear for the bending moments at free ends, that is A and B, that is equal to 0. That is MA is equal to 0 and MB is equal to 0. These are the fundamentals for the simple supported beam. That is at the supports, the moments created, all the forces should be equal to 0. Hence MA is equal to 0, MB is also equal to 0 now. So in order to draw the figure now, first of all draw the horizontal lines. First draw the vertical lines to pass through the various section of the beam now, where the forces are acting. Generally that's preferable now. Draw the horizontal lines to represent the length of the beam A and B. And the moments created by forces at D is required now, as well as the C also required now. Here I am taking the moments at a point D now. At D means here according to, since the beam is in equilibrium, with respect to the D point, the moment created by the forces toward the left side should be equal to the sum of the forces, sum of the moments created by the forces which are acting on toward the left side should be equal now. That is toward the moments toward the right side should be equal to the moments which are acting toward the left side should be equal now. So here now at D now, this I am taking the moments created by the right hand side forces now. To the D now, only right hand force is nothing but the reaction force is acting now. The moment is equal to now 5 into the distance is given now, it is equal to 2 meters now. That is here MD is equal to, simply we can take it as 5 into 2 now, which is equal to 10 kilonewtons meters. It is there now. But its effect is sagging effect now. Hence the bending moment is that it is positive now. Or in other words, MD is equal to, we can take it as 5 into 2 is equal to 10 kilonewton meter. Similarly, MC, that is bending moment at a point C, we can take the reactions at a point here now. That is AD is equal to 4 kilonewtons. That is MC is equal to, we can take it 4 into the distance is equal to 2 now between these 2 points. Hence it is equal to 8 kilonewton meter now. So after determining MC values as well as the MD values now represent the distance by using some suitable scale now. Because of point loads acting, the bending moment varies according to the straight line law only. Hence, after representing bending moment at C now, 8 kilonewtons meter, just join the points by using straight lines. From B also, draw the line like this. After that, the remaining points again, you have to draw the straight lines. This diagram is representing the bending moment diagrams. Okay, this is nothing but a brief introduction regarding the shear force for the bending moment moments diagrams for the cantilever beam when it is subjected to the point loads as shown in the problems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.